science teacher. And my physics students and pre-engineering students were working on how to translate what they were learning into real-world applications, because there were no free legal places for kids to skateboard or rollerblade in the nation's capital. And the solution was to build it ourselves. The building idea that we based this on was seen at a research facility in Mexico, where they built a building out of all tires. It's a concept called earthship construction. So we thought about it for a while and were able to come up with some ideas that we might be able to use it to build a skate park. A good skate park is all about feel. There are a lot of different types of skaters and a lot of different styles. Some people like quick transitions, some people like flow, some people like to go fast, some people like to do tricks. The bottom line with all of it is, how do things feel when you're riding them? It's an intuitive sense. There are a lot of physics concepts that go into riding a skateboard. Acceleration and gravity and friction, and then you get into the interplay with the geometry of the structure versus your equipment versus the rider. Each rider is unique, and each rider prefers a different width board, a different length of board, a different type of truck, a different geometry within their trucks, different size wheels. What feels good translates into a general shape and structure. There's a certain radius that feels better, a certain shape to the curves, there's a certain geometry to the hips and the angles that translates into better speed. When we first set out to begin building this structure, a whole team of us with a great deal of skateboarding experience got together and had a Play-Doh party. We were looking to build scale models. We were trying to represent them as closely as we possibly could, how the geometric shapes would factor in, in relationship to one another. The geometric shapes that we're dealing with are mainly spheres, portions of spheres, either a quarter of a sphere or a half of a sphere, depending on the area, combined with cylinders, all put together to create one big structure, each one being unique. We're building models because we all understand the geometry of what rides well intuitively. So the natural progression was to take that intuitive sense and translate it into something three-dimensional. It incorporates a great deal of geometry and even some trigonometry. When you're doing measurements for how much concrete are we going to need, you're going to bring in algebra as well as geometry. Once we got the Play-Doh scale model, our next step was to figure out what our materials were going to be. So math again came into the picture. We also had to figure out three-dimensionally, using real measurements, how many tires we were going to need. The structure is built with tires stacked like bricks, one on top of the other. The tires are put into place in approximation of the shape with the tires. After that, the dirt is brought in to truly form out and refine the shape. Then we lay down rebar, which is these long tubes of metal that reinforce the concrete, and then pour the concrete on top of that. Our calculations for the amount of tires that we were going to need and the amount of materials came from taking a general average of automobile and light truck tires. Now that changed after we began construction, and then we switched a short time through our project to heavy-duty truck tires. So that changed all of our estimates. It actually changed the design of the bowl a little bit because we were constrained by these different size tires. Since this is a unique project that's never been done before, there was a great deal of trial and error that took place. You're actually feeling it and working on it since it's never been done before. It happens on the fly.